So we saw the properties of Fourier transform and some examples and some problems. Now we'll see a short Matlab demo. First, what we'll do is we'll generate a rectangular pulse and see its Fourier transform. So we already know how the Fourier transform of rectangular pulse should look like. Basically, we should get a sinc pulse. So what we have here on the top left is the real part, top right is the imaginary part, all in the time domain, and the other figures in the bottom of the top row is the even and odd part of the rectangular pulse. Clearly, the rectangular pulse is already an even signal. So the even part is the rectangular signal itself, and the odd part is 0. And the real part contains a rectangular signal because there is no imaginary component. So this is the rectangular pulse in the time domain. We are observing it from -2 seconds to 2 seconds, but it actually extends from -infinity to +infinity. And the duration of this rectangular pulse is from half a second to -half second. So given this, if we generate the Fourier transform, how should it look like? It should look like a sinc signal, right? And that's exactly what we are seeing here. The big graph here is the spectrum, which is basically the magnitude plot. And we should be able to even notice where the zero crossings are. So in this case, we can zoom in and see where the zero crossings are. And as you can observe here, the zero crossings are at 2 pi. And what would be the corresponding real part, imaginary part, and the even and odd part of the spectrum? So this is a real signal, which means the frequency transform should have a conjugate symmetry in it. So the conjugate symmetry, so if we plot the conjugate symmetric part, then we'll have to plot, it's a complex signal. In general, it could be a complex signal. So if you want to plot the conjugate symmetric part, then you'll have to again either plot the real part or imaginary part or the magnitude and phase. So instead here we have plotted only the even and odd, and that is okay here because the given signal in the time domain itself is real and even, which makes it also conjugate symmetric, which means the Fourier transform is also real because the given signal is even, that is conjugate symmetric, real and even. So because of real and evenness in the time domain, the Fourier domain is also now going to be a real signal. So you can clearly see that the Fourier transform in the real part has the sinc pulse and the imaginary part is almost 0. Here you have to see a straight line. Some numerical errors are there, so you are not seeing, you are seeing some small values. It's basically 0. So this confirms our study of the properties where we saw that the real part will give a conjugate symmetric part. When it is real and even, it is obviously conjugate symmetric. So the Fourier transform should have the real part, which is exactly equal to the sinc function. And we saw the sinc function equation, and from that we are seeing even the zero crossings are exactly matching with what we have. And if you see the even part is exactly the Fourier transform here. So the magnitude of the even part is plotted here. And that is once again matching with our theory, because if the time domain signal is real, then we should see only the even part in the Fourier domain and the odd part should be 0. And that's exactly what is happening. So we can check the other properties by simply scaling this. If we scale this, what should happen? Let's say we just scale this by 2. Then everything should get multiplied by 2 because of linearity. Let's see if that happens. That happens. Earlier it was 5 in the spectrum here, now it becomes 10, and everything just gets scaled accordingly. So the linearity property works as such. Now what if you do a time shift? So let us say we shift it by, in this case, 10 times, in this case 0.1 second. So when you shift the rectangular pulse by 0.1 second, the symmetry is broken. We remember time shifting does not retain symmetry. So the symmetry is broken. So we don't get an even signal anymore. Now we have a real signal, but it is not even, which means it's not conjugate symmetry, which means the Fourier transform will end up being a complex signal. So it will not have only purely real part, it will have both real and imaginary parts. And that's exactly what we are seeing here. So we are seeing both the real part and imaginary parts to be non-zero, whereas the magnitude plot, if you plot that, that still remains the same, nothing changes. Remember, time shift changes only the phase. So the magnitude should not change, and that's exactly what is happening here. The magnitude has not changed, that's still the same. The phase has changed, As a result, there is a real part and a non-zero imaginary part. We are observing that. And if you see the even part or the conjugate symmetric part of the signal, that still exists because the original time domain signal is real, which means the Fourier transform should have only a conjugate symmetric part. So we see the conjugate symmetric part here as such. Basically, the magnitude of the conjugate symmetric plot is given here, and the conjugate asymmetric part is 0. Okay, so that we are still observing as such. So whatever we have here is the conjugate symmetric part, and what we have here is the conjugate asymmetric part. So what if we scale in time, right? So let us say we scale in time by 2 times. Let's see what happens. So if we scale in time, then in this case what we have done is we have compressed the time domain, which means in the frequency domain it should expand. Let's see if that has expanded. Clearly from observation we can see it has expanded, but let us see if it has expanded by twice. So now we are seeing this at 4 pi, 12 point something, which is equal to 4 pi. So clearly this has expanded twice in the frequency domain. So we compressed the time domain, and that has resulted in the expansion in the frequency domain. So and all the other properties are exactly the same. So now let's try and see what happens if we generate a triangular pulse. So we know that the rectangular pulse is supposed to give a sinc function. What is the Fourier transform of a triangular pulse? It is sinc squared, and that is exactly what we are seeing here. So the real part itself is showing a sinc squared. It is squaring the sinc pulse, and we saw why this is sinc squared. Now let us see the Fourier transform of a phasor. Let's say our signal has only a phasor e power j omega t. In this case, let's say omega is a single frequency. Let us set that frequency to be maybe pi, so that it is easier to see what is happening. So now what we have done is we have picked a phasor which is e power j pi t. Okay, so what is the frequency of this phasor? It's pi radians per second. So it has clearly a real part which is cos, you can see that, cos pi t, and there is an imaginary part which is sin pi t. That is also clearly visible here. So now we have a complex signal, which means now the Fourier transform should have both the conjugate symmetric part and the asymmetric part. In fact, the conjugate symmetric part should correspond to the real part, and the conjugate asymmetric part should correspond to the imaginary part. And is this an even signal or an odd signal? So in this case, only the even part of the time domain signal is plotted. The odd part here is actually imaginary. That's why it's not reflecting in this plot, because we can plot only real signals. So the magnitude could have been plotted, but here the odd part is not appearing because it's imaginary. Okay. So there is an odd component. So this is neither an even signal nor an odd signal. This is conjugate symmetric. This is not conjugate asymmetric. Because this is conjugate symmetric, we know that the Fourier transform should contain only the real component. There should not be any imaginary component in the Fourier transform. And what should be the real component in the Fourier transform? It should basically be an impulse, right? Because this is just a phasor and nothing else. And that's exactly what we are seeing in the Fourier transform. There is just an impulse at one particular frequency. And what should be the frequency? Because here we have chosen the frequency as pi radians per second, we should also see an impulse at pi radians per second. Let us see if we are seeing that. So let us just zoom in where this peak is observed. As you can see, the peak is observed at 3.14 something, which is exactly pi. So we are seeing a peak at exactly pi, which is the impulse at peak. Okay, so we are seeing an impulse at peak, denoting that this is a phasor which has just one value, which is an impulse at the frequency pi radians per second. Once again, it is also real, so we are seeing only a real plot. The imaginary plot is 0 because there is no imaginary component, as this signal is conjugate symmetric. And here clearly we have the conjugate symmetric part corresponding to the real component of the time domain signal. So it should be basically the magnitude of the spectrum of cosine. the cosine contains two peaks, one at plus some frequency and minus frequency. Here the frequency is pi, so we should see a peak at plus pi, another peak at minus pi. So if we zoom in, we should be able to see that. So that's once again exactly what we are observing here. So there is one peak at plus 3.14, another peak at minus 3.14. This is once again the spectrum of cosine signal, and that's exactly what we are seeing, because the conjugate symmetric part corresponds to the real part of the signal. And once again, the conjugate asymmetric part should correspond to the imaginary part, which is sine. For sine also we have two peaks, but one peak will be in the opposite direction. The peak corresponding to the negative frequency will be in the negative value, but because we are plotting the absolute value here, both appears on this side. So if you plot the phase, then you will see that there is a difference in the phase plot for this conjugate symmetric and the conjugate asymmetric part. Now let us see what happens if we plot an asymmetric signal, the signal that we used to regularly work with. So this is the asymmetric signal. It is real, so it has zero imaginary part, and it has an even component and an odd component, which is given like this. So its Fourier transform is some weird shape. So clearly this is not containing any kind of symmetry in the time domain, because of which you will have both the real part and the imaginary part in the frequency domain. That makes sense, because when the conjugate symmetric part and the conjugate asymmetric part both are non-zero in the time domain, then the real and imaginary parts in the Fourier domain will also be non-zero, and that's exactly what we are seeing here. And because in time domain this is only a real signal, we are supposed to see only a conjugate symmetric part in the Fourier domain, and the conjugate asymmetric part should be 0. And once again, that is exactly what we are seeing here. So the blue curve here corresponds exactly to the real components Fourier transform. Okay. And as you can see, this black curve and the blue curve here in the Fourier domain exactly match with one another, because the conjugate asymmetric part is 0 in the Fourier domain. So once again, you can feed in different signals here. So you can just change this to any signal that you want and observe its Fourier transform and see what happens to it when you shift in time, when you change when you scale in time, when you change any other parameters, and then you can observe its Fourier transform, see what happens to the symmetries and so on.